Hello, my name is Kevin Hartwell. I'm a sophomore ECE student at Wayne State, and I am making a tutoring video for MAT 2150, also known as DiffyQ and Matrix Algebra. I took this class in winter 2025 with Professor Sheng Zhang, and the topic for this video will be comparing two methods for solving second-order ordinary differential equations, that being the method of undetermined coefficients and variation of parameters. So, to start us off, I want to talk about what these two methods have in common, first of all. We know that a second order differential equation is going to take the form ay double prime plus by prime plus cy, and that's going to equal a function of x. And we know that if this function is equal to 0, then it's a homogeneous differential equation. And if it's anything other than 0, it's non-homogeneous. So by now, we should know how to solve it when it's homogeneous. And what these two strategies allow us to do is make solutions for non-homogeneous differential equations. So the solution y will take the form of the homogeneous solution when f of x would be 0, but we're also going to add a particular solution denoted y sub p, and that way, no matter what f of x is, we should be able to create a complete solution that incorporates the homogeneous and the non-homogeneous part. So the differences between these two, this is what's in common. Now, for the method of undetermined coefficients, we actually don't need the homogeneous part. So I'll say we don't need homogeneous solution to find the particular solution. There's a way to get around that. And I'd also like to say that the undetermined coefficients is usually easier and faster compared to the variation of parameters. Lastly, it only works for a specific class of functions for f of x. It only works in special cases. We'll get into what those are in a moment. And next, I want to talk about variation of parameters and what that entails. So for this strategy, you do need the homogeneous solution. Furthermore, it's definitely a little bit harder and takes longer to do. And finally, this strategy works for any function of x. So there's a trade-off here. Typically, if you can, you're going to want to do undetermined coefficients, especially to save time on an exam. But if you see a function that doesn't seem to work, then you're going to need to switch and do variation of parameters. So it's good to be capable of both strategies. Oh, furthermore, the method of undetermined coefficients, I'll give us an example problem here. This is one that it could work for. See, y double prime minus y prime plus 9y equals 3 times sine of 3t. So in this case, the reason why method of undetermined coefficients would work here is because the f of x function is a product of constants and trig. That is a part of the group of functions that it will work for. In fact, MUC works for any product of functions that include the following. MUC works for exponentials. It works for trig functions, sine and cosine. And it also works for polynomials. So this would be something like e to the x. This would be just sine of x, cosine of x. And polynomials would be any group of terms like that. So, as you can see, this is a constant and technically a polynomial, but it's also a constant. And then this is a trig function, so we can use the method of undetermined coefficients. And so, let's get into that. So first, we're going to want to write a guess for our particular solution. We see that it has a trig function inside it, so it's going to need to take the form of a cosine of 3t plus b sine of 3t. Okay, the reason it is this way is because we're about to take the derivative of this particular solution, and once we do that, we can plug it back into the original equation and figure out what a and b are. So let's do that. We're going to take the derivative of y sub p. It's going to be negative 3a sine of 3t plus 3b cosine of 3t. All right. The t doesn't matter. I wrote x on the right, but it doesn't matter what variable you call your input variable. And then we're going to take our second derivative, because this is a second order diffeq. It's going to be y sub p double prime equals negative 9a cosine 3t. And then minus, because the derivative of cosine is negative sine, minus 9b sine 3t. Awesome. So now all we need to do is combine these two in accordance with our beginning equation. So we're going to have yp double prime minus y prime plus 9y. And these are all sub p's. So we're going to just rewrite them down here. Start with y double prime minus 9a cosine. I'm going to ignore the 3t's just to save some space, but that's cosine of 3t minus 9b sine of 3t. And then we're going to do minus y sub p prime, which is negative 3a sine plus 3b cosine. And then lastly, we're going to add 9 of the y sub p normal. So plus 9 of the a cosine 3t plus b sine of 3t. Cool. Then we're going to simplify this down. First thing I notice is that there's a 9 distributed to both of these terms. They're both being multiplied by 9. And then they have the opposite sign of these first two terms. So this 9a cosine cancels with this negative 9a cosine. This 9b sine cancels with this negative 9b sine. And we're left with this quantity, which will be 3a sine of 3t minus, because this negative distributes as well, minus 3b cosine of 3t. And because we plugged it back into this original equation, we need to write the equal sign and what's to the right of it. So that's going to equal 3 sine 3t. So now that we're here, our undetermined coefficients of a and b have to equal some value to get us 3 sine of 3t. Well, we can see by inspection that b has to be 0. b equals 0 because there's no cosine on the right term, so there should be a cosine on the left term, on the left side of the equation, sorry. And we can easily see that a should be 1, because that way you get 3 sine of 3t minus 0 equals 3 sine 3t. Perfect. So now we have our coefficients. And all we have to do now is plug these coefficients back into our original particular solution. This is the form we guessed the particular solution would look like, and it was good because now we have an a and a b value. So our final answer for the particular solution is going to be y sub p equals 1 cosine 3t and then it would be a plus 0 sine 3t, so this is it. You don't need to write the plus 0. So that only took a few minutes to find the solution for our particular solution. And of course, you need to remember that the complete solution includes y sub p, but also the homogeneous solution. And the homogeneous solution involves you taking your differential equation, finding the characteristic equation, something like this, where the derivatives turn to quadratics, and that would equal 0. And then depending on what your roots are, you would find your C1 and your C2, and that can be found using an initial value. But this is what the method of undetermined coefficients is used for. It's used for finding the particular solution. Okay, but as I've discussed, this only works for a group of functions, and that is exponentials, trig functions that are sine and cosine, and any polynomial that's multiplied with them, and any other products of those groups. So you can have e to the x cosine x, you can have t squared plus 5 sine of x, because that's a polynomial multiplied by sine. That would work for method of undetermined coefficients. You could have e to the x over t to the 5th, let's say, because this is still a polynomial on the bottom. Any one of these functions would work. But what if we had an f of x on the right-hand side that was non-homogeneous and looked something like natural log of x? Well, we don't know how to use method of undetermined coefficients because the derivatives of exponentials, sine and cosine, and polynomials are really easy to calculate and let us set up a system of equations to solve for a and b. But the derivatives of natural log of x are 1 over x, negative 1 over x squared, etc. And these are not easy to evaluate in a system of equations. Same thing with tangent of x. This, in other words, sine of x over cosine of x. Oops, let me rewrite that. Sine of x over cosine of x. You might remember that the derivative of this is secant squared of x, which is really difficult already, and this does not allow us to solve a system very easily. So what method are we left with? Let me say that these don't work. Don't work. MUC. All right. Oops. Don't work. And these do work. Awesome. Well, then we would have to use the method of variation of parameters, which I'll get into right now. So as you can see here, we have our second order diffie-q. I'll rewrite that really quickly as y double prime plus 0 y prime plus y equals tangent of t. So we can't set up our y of p right away because we have no idea what it might look like. We don't have a clue, unlike we did in the method of undetermined coefficients. We knew it would be a trig function of sorts, but here we're not entirely sure what it could look like. So we need to figure out what the homogeneous solution is first, and that could be very simple. So y of h, we're going to keep that up there, and we're going to find our characteristic polynomial, which is just r squared plus 1 equals 0. Solve that for r, we get r equals plus minus I. And then this very easily translates into y1 is going to be c1, and that's going to be cosine of t. And then y2 is going to be c2 sine of t. And then we can just combine them together to get our homogeneous solution. y1 cosine of t plus C2 sine t. Perfect. So now that we have this, this is our y1, and this is our y2. What we can do from here is now set up a particular solution that looks like this. It's going to be yp equals v1 of t times y1 plus v2 of t y2. Now what I just did was I just made up two arbitrary functions of t called v1 and v2. And these are going to help us find our particular solution when they're being multiplied to y1 and y2, which are also functions of t. We have y1 is cosine of t, y2 is sine of t. But because we introduced these two these two functions into our particular solution, we need to introduce conditions that allow us to solve a system. So there are a couple conditions I'm going to introduce, and that is v1 y1 prime, and v1 prime y1 plus v2 prime y2. That's going to be equal to 0. And then our next equation is going to be v1 prime y1 prime plus v2 prime y2 prime. That's going to be equal to f of t divided by a. Where did I get f of t and a from? Well, that's just from the original equation, which is f of t is tangent of t. That's f of t. That's our non-homogeneous part. All right. And then our a value is technically just 1, because a right here next to the y double prime, that's just going to be 1. So that entire right-hand side equals tangent of t. The reason we set up these conditions is so that when we differentiate our particular solution, similarly to how we did in variation of parameters when we took the derivative, this way we don't have any second derivatives of v1 or v2. We just keep it at 0 here, and when we do the evaluation again, it ends up being the first derivative the entire way through. It keeps our calculation simple. So now all we have left to do is plug in our values into this system we've created with these conditions. So if we remember, we have v1 prime, our y1 is cosine. v1 cosine of t. And then v2 prime, and then y2 was sine. v2 times sine of t. That's going to be equal to 0. v1 prime, and then y1 prime is negative sine of t, plus v2 prime times y2 prime, which is cosine of t. That equals tangent of t. Awesome. What's left from here is we need to figure out what v1 and v2 are. Right now they're in their prime form, they've been differentiated, but we can still put this system of equations into matrix form, and that will allow us to find v1 prime and v2 prime. So it'll look kind of like this. This is the matrix algebra portion of the class. We have cosine of t, sine of t. Oops, I don't know why. So y showed up here. And then finish the matrix. We have negative sine. Oops. Negative sine of t. And then cosine of t. This matrix. Then here are unknowns of v1 prime and v2 prime. And that's going to be equal to the right-hand side, which is 0 on top, and tangent of t on the bottom. Now you've probably learned a few ways to solve a system like this for our V column. But one way I like to do it, and it's pretty quick to do on exams as well, for a 2x2 matrix on the left-hand side, is to use Cramer's rule. It's very simple. So we use V1 prime. That's going to be equal to the determinant, and we replace the first column with the right-hand side. So the first column of this matrix turns into this column. That's going to be for, put that in red, V1 prime, V1 prime, and then that would be, back to black, 0 tangent of t, and then just the same second column, sine of t, cosine of t. Awesome. And then that'll be divided by our quantity d, and d is just the determinant of this matrix that we have initially. So then d would be that determinant, cosine, I'll leave out the t's for now, sine, cosine, down here, negative sine. This evaluates really easily to cosine squared of t plus sine squared of t, which is just a basic trig identity, that's 1. So d every time, this is going to be 1. So then we know that v1 prime, that is as easy as saying 0 minus sine of t times tangent of t. Perfect. And then v2 follows a really similar process. Just gonna zoom out a little bit, extend this page. All right. v2 prime equals, we'll do Cramer's rule again. That is going to be the first column is going to be kept the same. Cosine of t or negative sine of t. Then we replace the second column with the right-hand side this time. v2 prime, v2 prime. Sweet. That will be 0 tangent of t. And this again is over d, but we know that d is 1. So now we just have to evaluate this determinant, which is cosine times tangent. That's just sine of t. I'll write out the algebra so we can simplify it. Cosine of t times sine of t over cosine of t subtracted by 0 times negative sine t. That's just 0. So this gives us just sine of t. So now we almost have our particular solution. All we have to do now is take the integral of v1 prime and v2 prime. That will allow us to get v1 and v2 normally. I'm going to start with v2 because that one seems a little bit easier, but v2 is going to be v2 equals the integral of v2 prime dt, which is the same as the integral of sine of t. And that's just negative cosine of t. I'm not going to write a plus c here like we're used to doing for indefinite integrals, because if we had a plus c and we plugged that back into our particular solution for v1, it would be v1 times cosine. And the reason that's not useful for us is it's kind of already incorporated into our homogeneous solution. If we had a c down here next to the cosine, we also have a c in the homogeneous part that accounts for cosine. So there's no need to have two constants that account for the cosine value. So we're going to leave that as is. Here's our v2. Then I would just integrate for v1. v1 equals the integral of v1 prime dt, which is the same thing as integral of negative sine of t times tangent of t dt. Okay. And then this seems like a pretty intimidating integral, but this is exactly why we couldn't use method of undetermined coefficients, is because we would have something like this that we couldn't use a normal system to solve for. But using variation of parameters, if we can evaluate this integral, we can find our v1 for our particular solution. So let me double check what I have written in my notes. This can be converted really easily to negative sine squared of t over cosine. Take the integral of that dt. And then we use a trig identity to replace sine squared t with 1 minus cosine squared t all over cosine dt. A little bit neater. Over cosine. And then this evaluates to two different integrals down here. It's going to be negative of this entire thing. It's going to be secant of t dt plus, I guess it's minus the integral of cosine t dt. I got that by taking 1 over cosine minus cosine squared over cosine. That's secant minus cosine. And then these integrals are easily evaluated. That comes to negative of natural log secant of t plus tangent of t secant of t plus tangent of t, and then it was subtracted by integral of cosine is just sine, so minus sine of t. And then for simplicity's sake, I'll distribute the negative. Our final answer for v1 is sine of t minus the natural log, minus the natural log of the absolute value of secant t plus tangent of t. Cool. So now all we need to do is take our v1 and v2 and plug them all the way back in to our particular solution. So our final answer, again I'll rewrite the particular solution, equals v1 y1 plus v2 y2. So it's going to be equal to sine of t minus natural log secant of t plus tangent of t. That's our v1 multiplied by y1, which is cosine. And then that's added to v2, which was negative cosine of t, multiplied by our y2, which is sine of t. And this is correct, but it can be simplified a little bit further because we have sine multiplied by cosine right here. That's sine t cosine t, and we have a negative version of that, which is negative sine t cosine t. So when this cosine is distributed to these two terms, so p, they would cancel out. So we have this cancels with that. So all we are left with is negative cosine of t times the natural log of secant t plus tangent of t. And this is our final particular solution. So as you can see, this value we couldn't have easily guessed as we were able to for our method of undetermined coefficients. So our final solution would be y equals yh plus yp. So then it would be c1 cosine of t plus c2 sine of t, and then all of that subtracted by cosine of t times natural log of secant t plus tangent of t. We had no way of knowing what this particular solution was going to look like, so we used the variation of parameters to make up our own particular solution to solve this differential equation. So this concludes my explanation of variation of parameters and method of undetermined coefficients. Just know that this procedure would also work for a problem like this. It would just take way longer, and on an exam I would not recommend using it because undetermined coefficients lets you set up your system way faster. But yeah, thank you for watching. I hope this helped, and good luck in your class.